Okay, welcome to Math 150, Section 2, Lecture 25, give or take a little bit. What I want to do today is do a very quick introduction to GreenThm, Stokes-Tham, stuff like that, and then leave the rest of the time to review. The big difference between 150 and 151 is 151 covers GreenThm in much greater detail. If you're going into physics or engineering, this is something you really need to know. Most of you, ooh, that is a phone. All right, so somebody will owe Munchkins. You can email me about whether or not you want to do it for the exam, or if you want to do it on the class afterwards. All right, so the big difference is we spend more time on sequences and series. 151 spends more time on Gauss, Green, Stokes-Tham. I want to just give you enough so you have a sense of what they are, so that if you're ever in a situation in life where you need these theorems, you at least know that they exist, and you know a little bit of what they say, and you know how to look it up. Also, the method of explanation, I can't say proof today, explanation is going to allow me to review a lot of concepts from multivariable calculus that we've been doing, so it's a good review. So let's talk about integrating along a curve. So imagine you have some curve in space. We will almost always choose our curves to be oriented counterclockwise, so we travel with the region on our left. We'll often denote the curve by gamma, and we'll talk about integrating a function f along a curve gamma. If the curve returns to where it starts, it's a closed curve, and we'll often put a little circle on this to just indicate that this is a closed curve. Any questions on material like this would be in the optional sections on exams. It would be like, here's 15 things, define 6 of them. One of them could be state GreenThm. Not obviously on this exam that's coming on Friday, but that could be something on the final. So you will not have to answer any questions on this if you do not want to. Well, let's think a little bit formally what this means. This is integrating along some curve gamma, maybe f of s ds. And if you remember, how many of you have done lengths of curves in Calc 1 or Calc 2? How long a curve is. Right? These are painful calculations. And the reason is ds does not equal dx plus dy. It's dx squared plus dy squared square root. It's the Pythagorean theorem. Is when you want to talk about the little infinitesimal arc length, you have to be very, very careful. I'll give you a proof of why you have to be careful. I'll prove to you every curve has the same length. So this is a straight line. Let's say it goes from 0, 0 to 1, 1. What's the length of the straight line? Root 2. I'm going to approximate this with a polygonal path that's basically hugging the straight line. Imagine that the vertical and horizontal movements are at most epsilon, where epsilon is really small. Does this polygonal path do a really good job of approximating my curve? Yes. Yeah, with an epsilon. And I can make it even closer if I want. I can keep making it closer and closer and closer. What's the length of this polygonal approximation? Well, if I drop all the horizontal components downward, and I push all the vertical components to the right, I have this straight line on the bottom. What's the length of the straight line on the bottom? 1. What's the length of the vertical line? 2 is not equal to the square root of 2. This explains why you have to be so careful and why lengths are so painful to work with. So if I want to do this, what we do is we choose C of t to be the curve, or C of t, say, parameterizes our curve gamma. So it gives me a way of walking around it. So if I have a circle, I could take maybe C of t is cosine t sine t. Or I could take maybe C tilde of t is cosine of 2t sine of 2t. Where this one is probably going through it twice as fast, and I probably only have t going maybe from 0 to pi now rather than 0 to 2 pi. So there are multiple ways of parameterizing a curve. You hope that at the end of the day, the value of your integral doesn't depend on how you choose to parameterize it. And then what we would say is the integral of f ds along my curve would be the integral, t goes maybe from 0 to 1, f of c of t times the length of c prime of t dt. Yes?
Can you remind me what it means for a parametric?
So basically, it's just walking along the curve. So if my curve gamma here, c of t, if I start off at t equals 0, I'm here, and then as t increases, I just go around the curve once and only once, and I come back to where I start. Yeah. And so if I have a circle, here's two different ways of parameterizing a circle. We are not going to do that much with this in the class, but I want you to be at least aware of these ideas and these concepts. Okay, so this is the length of my c prime vector. So if you think about it, I have a curve like this. I choose a bunch of small time increments and see where I am on the curve. I do a polygonal line approximating these. And if I choose a fine enough mesh, this is a really good approximation. And if I want to figure out what's the value of the integral of my function, ds, well, I figure out what's the length of each one of these, which is going to be my c prime of t. And if you think this is going to be giving you, the square root of dx dt squared plus dy dt squared dt, where x of t, y of t, that's my curve c of t. When I bring in a dt inside the square root, they'll become a dt squared. Cancel this. Yes, I'm canceling symbols. So you should really view this as delta x over delta t squared times delta t, and then you bring in the delta t and it cancels. So this is a little bit of an abusive notation, but it's to try to give you a sense of why this is true. Okay? So if you look at this as delta x over delta t, then I can bring in the delta t inside, and it will cancel the delta t below, and I'll have the square root of delta x squared plus delta y squared. All right. So this is how you would do line integrals. An integral of a function along a curve. Now I could do a more complicated one. Instead of integrating a function that's just a number, I could integrate a function that returns a vector. And the question is, how would things change if we are now integrating a vector-valued function? So it's a very similar setup. And now what we'll do is maybe we'll say big F is PQ. And we use P and Q as their adjacent letters in the alphabet. If you want to be more pedantic, F of xy is P of xy, Q of xy. Sometimes I put an arrow over the F to just remind myself that this is a vector-valued function. So I can just quickly glance down at the paper and see what's going on. And then what we would have is the integral along our curve of f dotted with ds would be the integral of f of c of t dotted with c prime of t dt. Say t goes from 0 to 1. And we often would write that as p dx plus q dy. So it's important to understand what the notation is saying, and that we're trying to use just simple notation and not be overly pedantic and just write so much that we spend all of our time just writing things down. So by p dx plus q dy, this is what I mean formally. I mean, take my vector-valued function, evaluate it at point c of t, and take the dot product of that with c prime of t. But since I can view f as p comma q, and I can view this as dx dt comma dy dt, well, when I multiply things, I'll have p dx dt dt. Oh, that's like p dx. And just that's why notationally we write this. Okay, so view this as p comma q. View this as dx dt dy dt dt. and you'll get p dx dt dt, that's p dx. Q dy dt dt, that's q dy. This is just notation. Okay? Any questions on this so far? All right. So the question is, why do we care about stuff like this? So it turns out we can attack a lot of very useful problems with this. And so I'm going to state Green's theorem now. And I will state it initially for a rectangle, and then we'll talk about how to generalize this. So Green's theorem for a rectangle. Was there a question or? Okay. So, and I'll draw my rectangle like this. Here's the point AC, here's the point BD, so this would be the point BC, and this would be the point AD. So the integral of P dx plus Q dy is the double integral over the rectangle of dq dx minus dp dy dx dy. So this double integral is the same as this line integral. One reason we care so much about this is if you take q of xy to be 1/2 x, if you take p of xy to be negative 1/2 y, then this expression is just equal to 1. Question?
Why is the coordinate AB instead of AC?
Oh, sorry, it should be AC. I copied it wrong. Thank you. So if I take the special case of q is 1/2 x and p is negative 1/2 y, well, dq dx is just 1/2, negative dp dy is just 1/2. So this quantity is 1. So when I integrate this, I just get the area of the rectangle. And so I get the area of the rectangle is equivalent to this line integral. Hooray, we've discovered a new way to calculate areas of rectangles. All right. This is not something to write home about. This is not something to be proud about. We have a new way of calculating areas of rectangles. The reason we should be excited is that this theorem holds even if the curve is not a rectangle. And we can use this to calculate areas of more general regions. If you want, we can use it to calculate the area of the circle we talked about a moment ago. That's the power of this result. Is it allows us to pass from some two-dimensional integrals to one-dimensional integrals, or one-dimensional integrals to two-dimensional integrals. We saw when we were integrating e to the negative x squared, it was actually easy to bump that up to a two-dimensional integral and use polar coordinates. The big secret, since you're not going to take 151, I'll pass it on to you, is when you are giving problems to students, one of these calculations is usually easier than the other. So which one do you give the students? The hard one. So in fact, what would you love this expression to equal if you had your choice? 0. So if you choose something where this is 0, you give them this to do. And if they don't know Green's theorem, it's a pain. Well, let's talk, before we prove it, let's talk about what this might even mean, dq dx minus dp dy. And this will allow us to review a couple of things. So let's look at I, j, k, d by dx, d by dy, d by dz, p, q, and 0. And I'll add the two columns again because this is how we do our determinants. And let's just see what we get. So d by dy of 0 is 0. Next one would be d by dz of p is 0. P only depends on x and y. And then d by dx of q. Okay, so that one survives. So we get dq dx. And this is going to be in the k or in the z direction. Now let's go the other way. D by dy of p with a minus sign, that survives. D by dz of q, that's 0. And then d by dx of 0, that's 0. So this quantity can be interpreted involving cross products. And this is written as the cross product of our derivative operator with our function pq0. And this is often called the curl of the function. And this is very important in a lot of applications in physics and engineering. Instead of doing the cross product, you could also do the dot product. You could do dp dx plus dq dy plus dr dz. It turns out that you only have the cross product in 3 dimensions. You don't have the cross product in 4 dimensions. We can bump up something that lives in 2 dimensions by just saying, oh, just set the third component to be 0. And so you can still use the cross product in 2 dimensions. And it will just give you that this is coming up. But there's a nice interpretation to what's going on. And if you do anything involving fluid flow and whatnot, they'll talk about the interpretations of stuff like this. But just good to see a little bit of where the stuff is coming from. Okay. So we've at least now, we've stated Green's theorem. We have some idea of why it might be useful. We have some idea of how to interpret what's going on. Let's see the proof of this for a rectangle. So we have 2 integrals to do. We're going to start off with the area integral. So what class do you think we would need to make this proof very rigorous?
Linear.
Not linear algebra. Real. This is a day where you need real. When in doubt, if you want to make something rigorous, that's what real analysis is for. Okay? For the rectangle, I can actually make the proof rigorous. And it'll allow me to review a nice concept for multi. So we have 2 integrals to do, dq dx, dx dy, and negative dp dy, dx dy. Which do you want to do first? I'm sorry?
dq dx.
Yeah. I mean, we have to do them both anyway. All right. So let's do dq dx, dx dy. Now we're going over a rectangle, so we first integrate over x. X goes from a to b. Then we integrate y. Y goes from c to d. So your first choice now is, do you like the order of integration, or do you want to switch the order of integration? Do you want to integrate with respect to x first or with respect to y first? What do you think?
Y first.
Okay, why? Explain. Sorry, I should say explain.
Because dq dx doesn't depend on y. So that
No, q is a function of x and y. dq dx absolutely can depend on y. What you need to do is you need to find a function whose derivative is dq dx. So if I integrate first with respect to x, I'm looking for a function which, when I take the derivative with respect to x, I get dq dx. If I integrate with respect to y first, I'm looking for a function which, when I take the derivative with respect to y, I get dq dx. So if I try to integrate with respect to x first, can you give me a function whose derivative with respect to x is dq dx? I'm sorry? Not dq, just q. Right? This integral is just going to be q. So this will just be the integral y goes from c to d of q. Now I'm holding y fixed. I evaluate it at the endpoint x equals b. Well, I'll write it slowly. I'll write it as xy evaluated at x equals a and b, and then dy. Because this is the function, or this is a function that has derivative with respect to x, dq dx. Are there other functions? Absolutely. But all those other functions will differ from this by a constant. And when we subtract, the constant cancels, so I might as well choose this as my example. And now what will I get? I'll now get the integral y goes from c to d of q of by minus q of ay dy. And let's look at what's going on. Here's the rectangle again. Here's how we're traveling our rectangle. Here's A, C, BC, BD, and then AD. What's dy along the bottom? How much is y changing along the bottom of the rectangle? 0. How is y changing along the top? 0. So if I look, I have y goes from c to d, q of by. That's integrating q along this part over here. That's just the integral of q dy. Okay. Now I have negative QAY, so I'm going, y goes from c to d, I'm going up because I have the negative sign. That's the same as now going down. I can add in the integral of q dy along this side because that's just 0. I can add q dy along this side, that's just 0. This is going to just equal the integral of q dy. And then if you do the p integral, you will get very similarly p dx. So I'll leave that as an exercise. One thing that is worth noting is if you now do the dp dy dx dy, you want to switch the order of integration. And this is where you would use Fubini's theorem, and you'd say because the double integral of the absolute value is finite, you can switch orders of integration. Because it's a rectangle, you don't have to worry about how the bounds change. That's what's so nice about rectangles. If I switch orders of integration, I don't have to draw the picture and figure out what are the new boundaries. This is why we love polar coordinates and spherical coordinates. A circle in polar coordinates is a rectangle. A sphere in spherical coordinates is a box. It makes it very nice to change the integration orders. So this is the proof of Green's theorem in a rectangle. What I want to do now is just quickly highlight the idea of how you would prove it in general. Okay. So we know Green's theorem for a rectangle, and we want to push it to a more general region. So imagine we have something like this. So, general region. Let me start off with a rectangle inside. We have Green's theorem for this rectangle, correct? Let's draw a rectangle next to it. Do we have Green's theorem for this rectangle? Yeah. And then what do you notice about this interior wall? It cancels. We do it in two different directions. So we now have, it's true for this larger rectangle. Well, that's fine. It's still a rectangle. We knew that before. But now if I go and draw a rectangle down like this, now that's something fundamentally new. And this interior wall will cancel. So the idea is basically you have this growing sequence of rectangles that expands outwards to your whole region. And you can even see the hand waving happening. Right? This is where you need real analysis to make this rigorous. But what you do is you take like a polygonal approximation of just straight line segments. And then because these are straight line segments, I can now make these rectangles. And then with all the rectangles, all the interior stuff cancels, and then it pushes the boundary integral to just integrating along a polygonal curve. And then you need to show that the integral along that polygonal curve converges to the integral along the true curve. For the area, it's much easier. For the area integral, the amount we're losing as we get a better and better approximation is tending to 0. And so you can see that the areas converge. So this is a sketch of why you can extend Green's theorem once you know it for a rectangle to a more general region. And this shows you the power of looking at good special cases first. This theorem is actually generalizing a theorem from calculus. So what word must you include in the fundamental theorem of calculus if you want to get points from it? Area. Okay? So I'm going to give you a special case of the fundamental theorem of calculus. I'm going to integrate from a to a of f of x dx. What will this integral equal? I haven't told you what f is. Doesn't matter. It's 0. If you think about it, what kind of closed curves do I have on a line? Well, I can walk forward, and then I can walk back. I can go too far past. I can then walk forward again, and walk back again, overshoot again, go forward, go back, and eventually return back to where I started. Anytime I cross a segment in one direction, I must cross it again in the other direction and cancels it out. In one dimension, there's really only one closed curve, a point. Integrating along a closed point is boring. But once you get to 2 dimensions and higher, now you have the ability to have something interesting. There's these things called circles. And you can walk around in a circle and get back to where you started without ever crossing the same place twice. So for example, and this is where it's very important in physics, imagine I have a function that blows up at the origin. I'm thinking of gravity, a 1 over r squared force. I can integrate along a circle around it. And I can take maybe like a nice annular region that stays away from the center. And in that region, my function is well behaved. 1 over r squared is fine as long as I stay there. It makes sense to talk about integrals like this. And the fact that there's a blow up here means something interesting might be happening. If you allow yourself to have 3 dimensions, you could actually have a spherical curve. You could have like a hemisphere where you would have a curve where you never go through that. If I confine myself to the plane, I would actually have to have a singularity in the region of integration for the double area. So there's a lot of nice subtleties that can happen. There's a lot of nice things that can happen. But for physics, astrophysics, engineering, these are all important things to be looking at. We want to have these theorems at our disposal. They're generalizations of the fundamental theorem of calculus. But they're generalizations of a special case that's so boring, you don't really extract it in 1 dimension. You don't really talk about integrating a function from a to a. All right. So this was meant to just be a really fast blitzkrieg introduction to Green's theorem, just so that you've seen it, you know what it says, and again, it allowed us to review some of our concepts and see why we cared so much about proving them. Because if you do elect to pursue physics or engineering or chemistry in some places, you need to have these stuff available. All right. I want to do one last thing is I want to review, or actually extend a calculation we were doing with sequences and series and just isolate out the integral test. And then after that, the rest of the class will just be review. So we almost proved the integral test before. So assume we have a sequence an that's monotonic. So what this means is the sequence is either never increasing or never decreasing. So it can stay the same, go up, stay the same, go up, stay the same, go up. But once it goes up, it can never go down. Or if it goes down, it can never go up. So a lot of sequences we care about would satisfy this. We were looking at this when we were trying to show that the sum of 1 over n to the p converges if p is greater than 1. That's a nice monotonic sequence. As n gets larger and larger and larger, 1 over n to the p gets smaller and smaller and smaller. So we'll assume an is monotonic. Assume we have a monotonic f such that either for all n, an less than equal to f of n less than equal to an plus 1, or an greater than equal to f of n greater than equal to an plus 1. Then the sum, n goes from 1 to infinity, of an converges if and only if. So IFF means if and only if. If and only if the integral from 1 to infinity of f of x dx converges. So a sum will converge if and only if a corresponding integral will converge. If the integral diverges, the sum diverges. If the integral converges, the sum converges, and vice versa. All right. So I'm going to prove by example. I'll do this for an equals 1 over n. The argument I give you can really be generalized to any sequence. The hardest part of the integral test, well, there's 2 hard parts, I guess. One part is figuring out what the function f is, and then the other part is doing the integral. Doing the integral is calc 1, calc 2. Finding the f is calc 3. As a rule of thumb, always try sending n to x. This will work almost all the time. So we'll take f of x to be 1 over x. All right. So here's 0, 1, 2, 3, 4, n. All right. When n equals 1, the value of 1 over n is just 1. When n equals 2, the value of 1 over n is 1/2. When n equals 3, the value is 1/3. 1/4, not drawn to scale, 1 over n. I want to study the sum, say n goes, maybe m goes from 1 to n of 1 over n. 1 over n. I can write that as the sum, m goes from 1 to n of 1 over m times 1. Do you agree that I can just multiply all the terms by 1? Yeah. This is one of the two big techniques we have in math. We can multiply by 1 and we can add 0. On a great day, we do both. All right, this is not a great day. How can I interpret this? Can you give me a geometric interpretation of 1 over m times 1? In terms of an area, which we've seen this object earlier today. This would be the area of what? So 1 over m times 1 is the area of what object? A rectangle. With height 1 over m and base 1. So if you look at what's going on over here, the area of that rectangle is just the same as the contribution of the first term of my sum. It's just going to be a contribution of 1. Over here, the area of this rectangle is 1/2. The area of this rectangle is 1/3. And so I've got to be a little bit careful. And so here, and here's n plus 1. And it'll be 1 over n plus 1. And now if you look at my function, 1 over x, the function is going like this. The area under the function is going to be less than the area of the boxes. And so what I would have, let's make sure this stays in focus. Oh, yes. So if I integrate from 1 to n of f of x dx, that will be less than or equal to 1 plus 1/2 plus all the way up to 1 over n. Actually, I should really integrate all the way up to n plus 1, right, for that final box. But since it's a lower bound, it's still a lower bound if I drop that. It would just make my result a little bit better to include it, but I don't need it. This is a lower bound. So do we agree that if we look at the boxes like this, the integral is going to be a lower bound for the sum? Now we can do the other way. Now we want an upper bound. So rather than having our rectangles go to the right, we just have our rectangles go to the left. The advantage of being at the blackboard. So now I have my rectangles going like this. So this would be 1/4, 1/3, 1/2, 1. Do I want to integrate my function from 0 to 1? No, my function is blowing up. So I'll just add the area of that first box. Now the area under the function is going to be larger than the area of the rectangles. Yes?
What do you mean when you say it's blowing up?
I'm sorry?
What do you mean when you say it's blowing up?
Well, f of x goes all the way up to plus infinity at x equals 0.
Okay.
And so if I just integrate from 0 to 1, I'm going to get plus infinity. And that won't be useful. Because if I get an upper bound involving plus infinity, I have no information. So what I'll do is I'll just say, I'm going to integrate my function from 1 to n as before, and then I just have to add on 1 to make sure it's an upper bound. Because when I integrate from 1 to n, it's a upper bound for 1/2 plus 1/3 plus 1/4, so I just have to add 1. So then this will also be less than or equal to 1 plus the integral from 1 to n of f of x dx. So we've sandwiched our sum between the integral of f of x from 1 to n and 1 plus the integral of f of x from 1 to n. So whether or not the sum converges or not depends exactly on what happens to the integral of f of x. And so now we note that the integral from x equals 1 to n of 1 over x dx, this is just the natural log of x evaluated in 1 and n. The natural log of 1 is 0, so you get that this is just the log of n. And that will give you that the harmonic series diverges. Not only will it give you that it diverges, but it will give you an idea of how rapidly it diverges. If you sum the first n terms, it's approximately the log of n. With a little bit more work, we could get a slightly better result than log n, but this is good enough for a lot of applications. This is not too surprising based on what we saw before. 1/3 plus 1/4 was at least a half. 1/5 plus 1/6 plus 1/7 plus 8 was at least a half. Every time we double the number of terms, we increased by a half. So you could use that to see some kind of logarithmic relationship, but this makes it a lot clearer. So this is the integral test. So the only challenge, really, because most of the time just sending n to x is going to work, is to figure out what the integral is. So I'm going to end with a slightly harder example. And again, it's going to come down to, can you do the integration? So let's study the sum, and it goes from let's go from maybe 4 to infinity of 1 over n squared, 1 over n log of n squared. And the reason I want to be a little bit careful is, the log of 1 is 0. I don't want to start n at 1. The log of n is negative when n is less than when n is less than 2.7. So if I just start at 4, I know everything's going to be fine. And 1 or 2 terms doesn't really matter. So I want to figure out if this converges or diverges. So we should study the integral from 1 to infinity, and then what function do we want to use for 1 over n log squared n? What should we try? So what are your thoughts? Yes?
We do 1 over k.
So what function do I want? I have x goes from 1 to infinity. What function should I use? F of x equals what? Anybody want to tell me what function I should use?
1 over x log x squared.
Yeah. Your first step should always be wherever you see an n, replace it with x and see if that works. So this is going to be a nice monotonic function. It's going to be getting smaller as x gets larger. So I want to integrate 1 over x log of x squared dx. All right, does anybody remember how to integrate this function? Or any thoughts as to how we should integrate this function? All right, let me rewrite it. Integral x goes from 1 to infinity, log of x to the negative 2, 1 over x dx. If I write, yes?
If you let u equal log of x.
So if u equals log of x, then du is 1 over x dx. X goes from, I'm doing it from 4 to infinity. As x goes from 4 to infinity, u goes from the log of 4 to infinity. So the hard part is seeing the u substitution. When I rewrite the algebra like this, it's much easier. This is the hard part. It's recognizing how to rewrite things. And see, when you have a log of x, its derivative is a 1 over x. So the 1 over x here I like, and I want to put that 1 over x with the dx. So this becomes the integral u goes from the log of 4 to infinity of u to the negative 2 du. Well, the integral of u to the negative 2 is u to the negative 1 over negative 1. That flips the order of integration. So you get 1 over u at the log of 4 at infinity. It's 1 over the log of 4. It's finite, so the sum converges. If instead of having log squared, I just had n log n, then I would have a u to the negative 1 here. The integral of that would be the log of u, and it would diverge. So the sum of 1 over n log n diverges. The sum of 1 over n log squared n converges. You can keep playing this game. 1 over n log n times log n converges, but 1 over n log n diverges. And you can make it as close as you want. And it just becomes a more involved u substitution. Yes?
Sorry, why again did you switch the log before and the infinity when you were integrating?
Because when I integrate, what function has derivative u to the negative 2? It's u to the negative 1 over negative 1. And the negative 1 here allows me to switch the order of integration. The other thing is, you know that this is a non-negative function, so its integral has to be positive. And so if I did in the other order, I would have a negative 1 over log 4. So I know I've got to switch the bounds. Yes?
Isn't the sum greater than the integral in this situation?
Well, it could be greater, but it'll only be greater by maybe 1 or 2, some small finite number.
Okay.
And that was the whole point. It's already been erased. But when we shift the boxes to the left or to the right, because all of our series terms and our functions are monotonic, we're going to only, we'll win, except maybe in that first extra box which we have to add back, or we'll lose except for the first box which we add back. And so I agree that the sum might be a little bit larger than the integral, but it won't be larger than, by more than 1 over 4 log 4 squared. And so they either both converge or they both diverge. Okay. Any other questions on this? Okay, so for the rest of the time, I want to just use it for review questions for the exam. So the first one I was asked about was vertically simple and horizontally simple regions. So I always forget which one is which. So the idea, I think, of vertically simple is I fix an x and I walk up. I enter the region, I stay in the region, and then I exit and I never return. And horizontally simple is I fix a y, I walk horizontally, I enter the region, stay in it, and then I leave and I never return. And when you're in a situation like this, you have a lower curve and an upper curve. Where you enter, where you leave. If you had a more complicated region, what you would often do is you would break it up into smaller, simple regions. And so in this case, here is my boundary curve. So I'm fixing an x, and I'm walking up like this. So I'm trying to figure out what is my range of y. So I would have, this would be my curve y1 of x. You give me an x, and this gives me the lower bound for where I start. And then the top would be y2 of x. And if this is a and this is b, then I would have the integral x goes from a to b, the integral y goes from y1 of x to y2 of x, f of xy dy dx. So the hardest part about these problems is figuring out what the boundary curves are, and then choosing an order where you can actually do the integration. If I give you a problem and the integration is not working, what should you do? Switch. And if that doesn't work,
Try the first one again.
there's something I would do before trying the first one again. Maybe change variables. And look and see, does this look like a problem that only depends on x squared plus y squared plus z squared? If yes, I'm thinking spherical. Does it depend only on x squared plus y squared? If so, I'm thinking polar. So you might even want to just do that first and just look at this problem and say, oh, I'm integrating over a sphere. I wonder what I should integrate with. Okay, it's kind of hard to hide when spherical coordinates should be used. Okay, when you have more nasty regions like this, almost surely changing variables is not going to help, unless you're doing a u substitution in one of the Calc 1 integrals. So try an order. If it works, great. If it doesn't work, try the other one. Yes?
So are you saying that's vertically simple?
So I would say this one is vertically simple, is that once I enter, as long as you draw a picture and tell me what you're doing and explain it in words, I don't care if you mix up vertical and horizontal.
Is it also horizontally?
So this one I think would also be horizontally simple as well. That you enter and then you never leave and come back. So this would be a region that's both vertically and horizontally simple.
What would be an example one that was like just vertically and not horizontally, or like just horizontally and not vertical?
Okay. So I was going to say, if I do something like this, like the Star Trek symbol. Okay. As I come up, well, the Star Trek symbol has a little bit of an asymmetry, but we'll ignore that. As I come up like this, this would be vertically simple. But it would not be horizontally simple, because I would come in, and then I would leave, and then I would come back. And so it would be nicer to do this by first fixing x and then integrating with respect to y, and then I have just one clean boundary curve. But it might be the case that it's better to do the integration the other way. So what you might do is just cut the region in half and do it as two different integrals, and maybe it's easier if you do the x integration first, not the y integration. And if that's the case, you just break up the region. But the hard part is the algebra. So for some problems, again, I write all the exams at the start of the semester, so I have no idea what is on the test right now. It might be easier, or you might just be asked to just set up the integration. And then you might be asked, as a separate part, do the integration. I know in the first exam, that's what we did for the Cam-Kayla problem. You was set up the problem to study, find the derivatives and whatnot, and then for extra credit, actually solve it. So the big step is, can you actually set things up? Once you have it set up, it's then a Calc 1, Calc 2 game. Well, that's not something I'm responsible for. You're responsible for knowing Calc 1, Calc 2 before you come here. And so I've tried to design the grading so that I can separate out what is your success in Calc 3 versus what is your success in Calc 1, Calc 2 entering Williams. Or if you've taken 140 here or 130 here from those classes. All right. We have time for maybe 2 more questions. Yes?
You do level sets?
Sure. So level sets is basically just looking at all inputs that have the same output. And so we've seen applications of level sets when we're trying to do the chain rule. So level set. So maybe I give you f of xy is e to the x squared plus y squared times 1 over x squared plus y squared. And I want to ask, what is the level set of this? So I want to say, for a given C, find all pairs x and y such that f of xy equals C. So if you look at this, there's some values of C that just can't happen. Yes?
X1 can't be 0.
I'm sorry?
X squared plus y squared can't be 0.
Well, I'm asking for values of C. Are there certain values of C that there will be no choice of x and y, such that f of xy could equal that C? If I give you C equals 4, 0, negative 8, 12, which possibilities? What can you tell me about this quantity here? What kind of number is it? Yes?
Positive.
It's positive, right? Unless x squared plus y squared is 0, in which case it's plus infinity, but this is clearly positive. This is not going to be 0. This is not going to be a negative number. So if C is less than or equal to 0, the level set is empty. There is no level set. There are no points x and y such that this is equal to C. All right, well, let's try to solve then maybe for C positive. So assume C is greater than 0. So you want to solve, and I'm going to do it e to the r squared times 1 over r squared. Right? Where r squared squared is x squared plus y squared. So the question is, can you always solve this? Is there always going to be a choice of R that works? Yes?
R can't equal 0, right?
R cannot equal 0. So if R equals 0, this blows up to infinity. Now, as R gets closer and closer to 0, this part over here is getting closer and closer to e to the 0, which is just 1. But then I can magnify this by anything I want. So I think I can get any value of c greater than or equal to 1. Or maybe greater than 1. But what if c is less than 1? What if c is equal to a half? Is there going to be a solution for that? So to some extent, you almost want to say, what's the minimum value of this? So I'm giving you a much harder problem than I would give you. What if I study f of u is equal to e to the u divided by u? I could ask you, what's the smallest value of this function? And just let u equal r squared. Do you think you can make this function equal to a half? And here we are restricted to u being greater than or equal to 0. Well, what's e to the u? E to the u is 1 plus u squared over 2 factorial plus dot dot. Ah, so e to the u over u is 1 over u plus 1 plus u over 2 plus dot dot. This can't get smaller than 1. So this is a hard problem. With a little bit of work, you can show that the level set will also be empty if c is less than 1. I don't think we can even get c equals 1. I think any c greater than 1 I think we can get, but otherwise I think we'll be in trouble. So this is a very hard problem. But break it up into parts that you can do. What can you say about this? Are there any c's that you can immediately eliminate? The other thing is, any number that's of the form e to the r squared times 1 over r squared you could get. So if I take c equals 5, I get e to the 5 squared times 1 over 5 squared. I know that level set is non-empty. And then that will be all the points x and y such that x squared plus y squared equals 5. Oh, that's a circle. So it is going to be a circle of a radius that's going to be a complicated function of c. Right, but break it up into small parts. Try to do the parts you can do. If you have any questions, feel free to shoot me an email.